Okay. I can talk about. I still haven't updated the list of problems, but I will try to do it before Thanksgiving break. So you just have that as some of the last problems that I add to the PDF, so that you know that you don't have to be working on new problems kind of like closer to the final period of the chance to like on your problems that you want. So some of the things that I need to include is kind of like this alternating optimization, like this alternating this works method, which is important to understand. And for matrices and for functions. And then one of the other topics I'll do before Thanksgiving. So today I'll tell you how to do optimization with the transfer networks, like how to do the gradient and all that stuff. Um, and then next week, I want to talk about the non-negative rank and the non-negative matrix factorization, which is a little concept as well, something like important applications. And it's related, it is another type of like, you know, compression speed because that is more when like no, all the entries of the matrix for the tensors are not negative. So you want to do a factorization with the products of non-negative matrices. And that's actually the one thing as well. Like there's this thing called like what's called latent semantic analysis for like analyzing topics in documents. So I'll try to do that before the break. And then after the break, we'll talk more about like applications because we're kind of like almost done in terms of like what is the main tool, but I wanted to discuss it. Um, that's kind of like the idea. But yeah, I'll try to update the problem, do like the final update um before Thanksgiving so that we have like a response. You want to have to reach to finish anything that you need. I'm probably should have like another day where I just kind of like help you out with problems to start something particular I want. Um, well, I think in the end, like just like upload all the solutions to the problems. Like if there were some students, mostly like the ones who were like PhD or like graduate students who if they wanted to do like a read like a specific paper and do kind of like a summary of that, they're working on that. I mean, if someone wanted to do that, they're welcome to, but I'm not going to like expect anyone to do that. So for me, it's kind of like as long as you do the problems, I'm happy. So there's no specific kind of project that I have in mind. I'll just try to update. There are a few interesting problems that I do want to, you know, um, put on the list. What's nice about this non-negative matrix factorization is that it's often related to linear programming. If you have like taken that class, where it's kind of like optimization problems where like the variables are non-negative. So that's kind of like the fun thing. But yeah, like I won't have like I mean, if someone wanted to kind of like look at something specific, I'm not going to force any of write a summary of something. Okay, so yeah, let me show you how to find the gradients and all these things for like the tensor networks, which hopefully should help you solve some of the problems I had written on the PDF. So did you say something, sorry? Oh, is it? Oh, oh my God. Thank you. I'm glad you're keeping track of it. That makes sense because yeah, like I have two or three staff already outside of that. Yeah. But, yeah, right. Okay, so kind of like the idea here is that let's say you have like a tensor that has been written in tensor training format. I'll just explain you the idea with a simple enough example because otherwise I can just we can keep track of tons of indices that don't add much to the understanding of what's going on. So let me just check my notes, which one I need for the calculation. Okay, well, I did it with three legs so that it was easier to understand. So let's say you had like a tensor. Okay, with three legs, and you do like a tensor train. The tensor, again, when you express it as a tensor train, kind of like each of the cores has one of the physical legs. So let me actually, okay. So I will need three cores here. I'll just use like a different color for like the legs that are like the virtual legs, meaning that those are the ones that are being summed over, right? Uh, those are the ones that are being summed over, and the physical legs correspond to these three ones. I'll introduce some notation in a moment, but let's say, do I have it? Let's see. Because let me just check how everyone feels. There, well, I'll call them FGH. Okay. And again, these come from doing SVD decomposition. These come when you do SVD decomposition, so these legs, the size on which they take values are given from by the branch of the SVD decomposition, which in principle could have been large. So kind of like one way to, so like, there are two options that you have. One way to kind of like compress the tensor, right, is that you kind of like truncate these ranks. If you do that, then like this is not really like inequality, it's more like an approximation, right? Like so, but that's kind of like more like a local compression because it's something more like kind of like that is related to this particular leg or this particular leg or the compression but for the truncation. A more kind of like global approach is to be like, okay, now let's just try to find another tensor, which I'll also write tensor training composition, which is just close to this one, in the sense of like the distance tensor that we have, but the legs of this other one being like the bonds being like smaller size. So the goal is that we want to find a tensor S. And again, I'll just think of it as being I don't know, there are names for the there are names for everything, but which is close to T, but now like these graphs being smaller, right? Like so the way I'm doing it is like I kind of like I fix the ranks ahead of time, and I want just to find like a tensor of those particular ranks, which is close to the given one. As I discussed, like there are all these variations schemes where like the rank doesn't have to be necessarily fixed ahead of time, but this is kind of like the easiest one to kind of like go like explain. Okay, so if you call these like rank one, rank two, where like where you start of a given R1, R2, which are thought of small, right? Which you think of as being small. No, like these legs are being paired in the sense like if you got, meaning like if this leg takes three values, then this leg takes three values. If this leg takes four possible values, like or like the indices go from 1 to 4 or whatever, like this one will go from 1 to 4. So kind of, so they're matching in that sense. Oh, yeah. See, give it R1, R2, small. Those that need for R1, so here, like, again, I can start with the T, right? I start with the tensor T is kind of my ink, right? Like you do the tensor train decomposition, right? And these legs, like the ones that I put in color, are the ones that are being subbed over, right? Yeah. And those came from like the SPD decomposition and from the ranks of the SPDs. So you have no control over those because they are just whatever the ranks of the SPD decomposition was, right? Yeah. So what I'm saying is like maybe those ranks were too large for your case, right? So you want to find a different tensor that is kind of like close to this one, right? But where these legs would be of a given size, you see? Like, so it's not, it's like you're trying to find a tensor close to, like each those types of smaller. Right. So, that each node has a smaller dimension in the direction on which they're being contracted. Yeah. Which is okay, like the matrix analog of that is kind of that's like actually what I did the matrix analog last week, which was you have a matrix A, right, and of a given rank, and you want to find a matrix B of lower rank that approximates it, right? So it's kind of like the same idea, but this is kind of like in a sense, like sometimes it is referred to as multi-rank, right? Because it's kind of like a sequence of ranks, so it's kind of like you're doing it like rank by leg by leg. Okay, and so again, T is kind of like my fixed data, and S is S is what I'm trying to find, but I'm kind of like thinking of it, kind of like to find S. Basically, since I'm thinking of it as being in tensor train format, really my unknown tensors are A, B, and C. So really, what I'm trying to find out is A, B, and C. So what I'm trying to find. So ABC is what I'm trying to find. And how are they trying to be found? The idea is that they are going to try to minimize kind of like the distance from the tensor to the one that I started with. So again, there is a function which I'll regard as being a function of A, B, and C. Which again, the 1/2 is just for convenience because there are like a bunch of like squares everywhere. So what I'm going to try to minimize is the distance squared from the tensor S to the tensor. But again, like I'm thinking of the tensor S as being determined by A, B, and C. That's why I'm writing a function of A, B, and C. No, like I mean, it's just like here, again, like these would be kind of like when you do like a tensor train decomposition, like the legs, like the legs over yours that you're summing along, those are kind of like the values of those legs that if they go up to 1 to 5, that meant that the rank of the SPV becomes. I don't know if you remember like the setup where we would take a tensor, regard it as a matrix, apply SPV, right? And when you have the SPV, you have this product of matrices, and let me just sorry, let me just write it like this. When you have the tensor we regard it as a matrix, right? And then you would apply M to D as and so that it would give you like the product of matrices. And if you think about it, like in the tensor notation, like the leg over where you're summing along that takes values up to R. Like it goes from 1 to R, so R is kind of like the branch that were showing up in the L22 decomposition, right? So here, like like maybe this goes up to value 100 and this goes to the value 50, and then you want like 7 and 8, like so that's what I'm trying to control there. So how large, like how much was like the rank of the LTV factor, right? LTV
Yeah, but then like that makes a lot of sense. But then my question was, so why are we trying to make it very simple?
Well, it's kind of like it's kind of like the same as that's also why it's useful to ask kind of like the same question for matrices, right? Like when you have when you just have like a matrix, when you do the SVD decomposition, right? Like the largest singular value is kind of like you construct the best features, like the most important features of the very like the data in the matrix, the matrix represents. So it is something analogous to that, where like maybe the most important features of the tensor are kind of captured by, it's kind of like a compression scheme, like you kind of like make this like a low rank, low rank approximation to the tensor, in the same way you want to do something similar for the. So it's kind of like, or you can just think about it as a least square type of problem for tensors, the same way for like the same idea. It's just that what I was saying is that literally, like because this is kind of like a sequence of ranks, like that's why sometimes it is called like a multi-rank, because it's not just like a single number, it's like one. But it is kind of like similar to trying to find like these low rank approximations. Okay. We can think about this as a low rank approximation. But that is useful for the same reason basically that is useful for matrices, like like you have to store less information, like and like it kind of like reveals like maybe like the more important features of that.
So we were talking about before, there's like infinitely many ways to deal with FGNs. There's infinitely matrices you can choose, but you restrict the rank, right? So let's say, like the rank between F and G has to be like some R, right?
Right.
If you want to completely express that tensor, like, what's like the fundamental property that allows you to do that? Like, do the sum of the ranks has to be the same? Like how do you make sure that like you're conveying the same information across all of your ranks? Like, do the ranks have to be the same?
Like, are you talking about T? Well, they don't have to be they don't have to be the same in either of them, right? In T, when you do the decomposition, like the ranks could be different, right? And same here, like when you're trying to find it, the ranks could be different as well.
So what's the commonality between different compositions for T then? It's the sum of the rank?
Oh, I see what you're saying. Okay, so well, there is there is a lot of flexibility in the decomposition. Like even like I I don't think there's anything in particular that it's not that the sum of the ranks have to be the same or anything like that. Especially because you can even do the like when you're doing the sequence of SVDs, you have to choose like at one leg, to matricize first, right? And so definitely like the right like the like if you get started with starting by I don't know like with the second leg and matricize along that leg, you wouldn't expect the branch to remain the same. So there is a lot of like ambiguity or like non-uniqueness in that sense, but kind of like that is not as bad as it seems, because like it's still like the representation again, like if you just did the count of that this was n to the e or whatever, like like and it becomes linear in n or something like that. Like that's what we have said. So that is like the biggest advantage. But it is true, that there's a lot of flexibility. So it's not that if you have to test a train decomposition for the same tensor, then the sum of the ranks have to be the same or something like that. I'm positive that that's not the case, right? Like, that, I mean, there are certain canonical representations, meaning like, that you can demand certain extra conditions on the tensor prime representation, but that's not enough to tune it down so that it's not a unique one.
How would you define the magnitude of those tensors to us?
Okay, so, okay, in the same way as how you do it for vectors, so what is like, it was with the inner product between tensors. So yeah, I was actually about to write it in the other way expression. So right, and so when you have tensors, you can just like do a dot product and just like joining the legs, right? Like the common legs, and that will give you a number. And then it goes like that. So that was the that is what you use then to define the distance between the tensors. Now, this population is very similar to the one I was doing last week because again, this is kind of like a dot product or a linear product. So you kind of distribute like just as before. Okay, so that gives you t with t. Okay. Oh my God, my brackets are the worst. So then minus 2, t with s, plus s with s. Okay, and so which of the negative sign for the s? Oh, it says minus gives you the plus, right?
Yeah. Yeah, I see.
Yeah. Now, again, t is known, right? So really, the first factor doesn't depend on t. I mean, you have like it is what it is. You don't care. So you're trying to minimize the distance. Really, what you're trying to minimize is this thing, and that's why you see like the 1/2 is useful because it cancels that too. So really, what you're trying to minimize. So what you're trying to minimize is okay, let's get rid of like okay, is minus, right? Like after I use this 1/2 to kill this 2. So this is this is what you're trying to make small.
That's
Oh, yeah, you're good. You're right. Yes, so 1/2 instead of 2 things. Now the thing is that each of these dot products or inner products has a nice representation in terms of the diagram. Because for example, what is the contract, like the dot product or the inner product between T and S is the contraction. You just join the physical legs. So let's start with the first term. Like so let's just try to interpret what is right, what is in terms of the diagrams T with S. So again, like what you do. Copy. And then you so basically what you do is like you stack, you join the legs. So like, here like it doesn't matter whether they're facing up or down. So just like I'll just change their location so that it looks okay. So that is a scalar, that is a number, right? The dot product. Okay. And again, I'm thinking of it as a function of A, B, and C. Okay, so this depends on A, B, and C. Now, what does it, so what does it mean to that it depends on A, B, and C? It means that it depends on the entries of the tensors A, B, and C. So meaning, so it depends. So it depends. Okay. And now here you'll come to appreciate why you have like all this like you don't like to label things when you draw the diagrams. But again, this is a way of representing a gigantic sum. So let's just write it down explicitly because I have to take a partial derivative in a moment, so I have to show you how it looks like. But that kind of like you feel, oh, this is why the notation is so nice because you don't have to see that humongous mess. Um, okay, so basically, whew, let's see. I'll call these legs I, J, K. I'm not, I'm starting with these ones because I'm going to take the partial derivative with respect to the entries of B. The reason why I'm going to choose B is because of the three that I have to choose from. Like A is kind of like a matrix, has two legs. C is also like a matrix, has two legs. So B is like the one that's genuinely like a tensor. So I want you to see how it looks like for like a genuine tensor. So that's why I'm kind of like prioritizing calling the legs of this one, I, J, and K. Um, and then the others, I'll just call them something else. So let's see. I'll use a different color just to again like let's call this one L, M, N, and then what? I don't know, P. I don't know, like whatever they are. Right? I care less about those because again, I will take the partial derivatives with respect to B to show you what I had promised that essentially if something where like the circle disappears, right? That it's not like flexible. So, okay. So this thing represents, so this represents the following sum. So I have oh my God. I got 1, 2, 3, 4, 5, 6, 7. I have 7 instances, right? Like 7 things. So it's a sum of 7 things. I'm not going to give them values or anything. Like, I'm just going to write it like symbolically as a sum over I, J, K, L, M, N, P. Okay. And now you see why by the way, general relativity people have like similar things with tensors and they just never write like the sum explicitly. So they have like Einstein summation convention where you don't write like sums explicitly and you just understand that it's implicitly repeated twice that it's getting added and then plus one because you don't want to be writing these things. It looks horrible. But let's say okay, let me read it like this. So this would be A. I guess it doesn't matter which one I call. I L. I'm going to kind of like go this way in the diagram. So A, I, okay, so A, this has like entries I and L. So it's contracted with B. So B has entries, let's say B, J, K. Okay, J, K. And then C has entries K, P, and H has entries P, N.
I mean, it won't be like you'll see that, all this mess, like it doesn't affect too much like the calculation, but I still want to show you how it looks like. And then G has entries like, okay, like I'll just call them like N, J, M. And then what am I forgetting? Just F, right? And F has entries, F has entries ML, I guess.
So you see, it is a fun, again, like the entries or like the coefficients related to H, G, and F, they're kind of like constant because like they are known. The things that are genuine variables are like the things involving A, B, and C, right? So this is a function like, if you want it to be kind of like more like in the calc3 perspective, this is a function of the entries of A, B, and C. So this is a function of the entries A, I, L, the entries B, I, J, K. Well, I mean, it's like a bad notation because like this is being summed over. So like maybe let me I'll just kind of like keep writing this as a function of, again, this is kind of like a function of the entries A, B, and C. Well, which I had before. So let's just keep it like this. Okay. Okay, and then
So that, so how should the those, it just happens.
well, right, that's the thing. Like the thing is like at the end of the day, this is kind of like an expression that's linear in each of the variables, right? So when you take a partial derivative, it's kind of going to be similar to, if you had a partial derivative with respect to x, I don't know, like a, b, c, x, y, z, or the x goes away, right? So that's going to happen. You just have to be a little bit careful because, like, just haven't set it up, but it's usually what's going to happen. So that's why it explains why it will go away, right? So let's say, okay, but this is a good moment just to kind of like show like a little bit of like proper notation. So if you wanted to take a derivative, okay, so now I want to take a partial derivative with respect to one of the entries of the tensor P. Again, I'm just going to do the tensor P because everything is the same, but this is the only one that's kind of like genuinely a tensor. Okay, so I'm not going to refer to the entries of these tensors as I, J, and K. I shouldn't call them I, J, and K because I, J, and K are being summed over, so it's kind of like a dummy index. So it's very confusing if you hold the entries I, J, and K. So I'm going to call them I bar, J bar, K bar. It's almost the same, but it is like the correct way of doing this. And so you think that
Oh my God. I'm so happy that you can just copy paste things on the iPad. I don't know how you would have done this in an actual class, like, chalkboard if you had to write this like over and over.
right. So yeah, these are just like regular partial derivatives. So anything that's not depends on b is kind of like a constant. Okay, and so you get the partial derivative of b I j k with respect to b I bar j bar k bar, and that's going to be like a delta chronic, or like a no.
Again, I want to go slowly. So, okay, I took out all the constants from the partial derivative, and then you just end up with the derivative of with respect to b I bar j bar k bar of the entry v I j k.
And again, like the better comparison to have here is like of what that should be is like if in top three you had called, if in count 3, instead of calling the variables x, y, and z, you call them like x1, x2, and x3, right? So what is the derivative of xi with respect to xj? Right? They're 0 if the variables are distinct, and they are 1 if the variables are the same. So if you let the product or delta. Okay? So it is the same logic here, but there are 3 indices, so it's like a delta product where like for 3 indices, you know.
Meaning that the is one only when the three indices match entry by entry. So like this will be. How did I call it? How did I write? Oh, yeah. Like I'll use kind of like a multi-index notation. So this would be delta of the the vector I var, j var, k var with the vector I, j, and k.
So that means that the only time you get something non-zero, the only time you get something non-zero is that if these match like entry by n. That then these match entry by n.
I guess it's slightly. Tough. X and I, it's not that. Really, it's a function of. Now,
Well, no, but it's kind of like the same, you know. That's why I was saying like it's similar to top 3, right? Like, you know. I mean, here's like a way.
oh, yeah, yeah.
This is something. Here's something someone might have said. They might say, "Oh, let me use the product rule here." And then this is like the derivative of the first function with respect to x times the second one plus x times the derivative of the second function with respect to x. But in top 3, you know, like since x and y are regarded as independent, this goes away, right?
Yeah.
So secretly, what you're doing, this is kind of like a fancy way of like rewriting, you know, when the variables are distinct, the partial derivative is here, right?
But we're differentiating this from I bar, j bar, k bar, right? So does that mean that whenever ij is within those vectors, but whenever it's within the tensor, that it's going to be 1?
Right. So the idea is like, this is a fixed value for, you know, I bar, j bar, and k bar are fixed numbers, right? So so you know, like you can give it like a specific entries just to make it more clear. You know, this is kind of like B24. I don't know. This is with respect to the entry B24, B124, right? So the idea is that in this gigantic mess, the only time that these derivative survives is literally when you had 1 to 4 at the top. Okay. So basically what that will make is all the sum, you know, originally you were summing over I, j, and k, but that's 0 except when I, j, and k agree with I bar, j bar, and k bar. So all the sums over I, j, and k are completely lost. And you can replace in these sums, you can kind of like get rid of these 3 indices, and just every time you see an I, put an I bar, every time you see a j, put a j bar, and every time you see a k, you put a k bar. So that's kind of like this, like, you know, it takes a while to get used to this like index notation, but that's like kind of like what ends up happening. So right, so what I'm saying is that there's no more sum over I, j, and k because that's always 0 except when I var I, j, and k equals I var, j var, k var. So you kind of like replace this with the vars. Oh, I'm glad that I use different colors actually. So that makes it easier to kind of see where the changes have to be made. Okay. And then you just want to do like a tensor diagram interpretation of this massive sum. And what I'm claiming is that it is what you get if you just had removed that let's just see that this gives you the same. So now the thing is like the sum is over L, M, N, and P. So there are three indices. Oh, sorry. Oh, sorry. You're saying that P shouldn't be in the sum, oh, here?
Yeah.
Well, but, let's see. Let me see if I'm getting confused. Well, the thing is like P corresponds to what you were contracting here, right?
I said B.
Oh, B. Oh my God, yeah. Oh, I see. I don't know why I was listening to. Yes, you're right. Yeah, thank you. I get you. Thank you. Yeah. Thanks. Yeah, you're good. Very okay, and it disappears, right? Which is supposed to happen. I'm glad you noticed that. Okay, but what I'm saying is that these, whatever this is, has three legs, right? Or three free indices, right? So whatever these represent something with three legs, which are free, and so it's like a tensor of order 3. Okay, so this represents a tensor of order 3. So this has three free indices. So an order 3 tensor. And it's kind of like easy to see. Let me copy paste. Let's copy paste this one. Like what happens if you just, what happens if you just take the tensor net, like, the tensor diagram that we were working with. Let's call this I bar, J bar, K bar, and let's just delete, just like erase that from the middle. And if you were to, if you were to write down the sum, you'll see, if you were to write down what that corresponds to, you see it matches like this gigantic sum. So it's a very nice notation, and for, you know, for representing this gigantic sum, it's kind of like a really fun visual rule for like a partial derivative. Yes.
So what's the reason behind like I and regular I take versus the I?
Oh, the thing, okay, so. Oh, okay, so it is similar to, like, just to give you like a comp one example, imagine that you have like a definite integral, right? Okay. Strictly speaking, you shouldn't write something like this, because the t's appearing in two places, right? Like as an upper bound and inside the integral, right? So if you wanted to find the derivative with respect to t of this thing, that could be confusing because you might think, oh, do I have to, take the derivative of, do I have to take a kind of like a derivative on the inside because this seems to depend on t? But really, like the solution to that is that you think, well, no, like the integration is kind of like a dummy index. That's how they're calling. You call them, right? So it doesn't matter what name of the variable you give, when you're integrating. And now it makes it more clear, that you're just integrating with respect to t, differentiating with respect to t, and like then the fundamental theorem of calculus just gives you t squared, right? So it's kind of like similar to what's happening here, because a sum is kind of like just a discrete integral. Like, that's one way to think about it. So you're kind of like integrating, like you're integrating in the I, J, and K variables, right? So it would be weird to take a partial derivative with respect to I, J, and K because they're being integrated over, or added over. So like you have to use a different name for the index that you want to differentiate against.
Yeah.
It takes some time to get used to it, yeah.
So I get like again, I think it represents like the indices in that.
Right. The thing is like IJ and K represent the indices, but they're being summed over, right? So it's kind of like this is kind of like B111 plus B112 plus B212. It's like a massive sum. So you cannot put IJ here because then it would be which IJ and K, they're all being summed over, you know what I mean? So you have to specify which one you have in mind. And that you can, if you put IJ and K is not clear because IJ and K are taking all possible values. That's maybe a better way of saying.
Yeah. So I feel like it's half the battle, right?
We still have the other one.
Partial derivative,
Yeah.
but you still define critical values or alternative to the last.
No, like, and you also, right, it's, yeah, and also I need to take find the derivative for the other term, right? Because like the function was a combination of two things, right? Yeah,
Ah,
yeah,
Well, I feel like we just apply.
Well, it's kind of like the same. It's just a little bit different because this is quadratic in S. So, like it's S with S. So when you write it down I'm about to write it down, but when you write it down in terms of diagrams, you have like in the sums, you have two components. The coefficients for B, for example, appear twice. So there you do have to do a product rule.
Yeah.
Yeah, and that's where like that is where it comes like the fact that I mentioned before that you can like get two times like the network because it's kind of like what is the derivative? I mean, again, always call one is like a good example. What what is the derivative of x squared? It's 2x, right? So it's kind of like you get the same but twice, more or less. Like you just have to be a little bit more careful, right? Because there are more variables around. But that's kind of like the same idea. But yeah, but the thing is like this is kind of like giving you like the tensor representation for the gradient in the direction of the tensor. So you can do kind of like a gradient descent. I mean, once you have like the other partial derivative, you can do kind of like a gradient descent in that direction. Because what I had mentioned in class last time is that usually it is more practical when you're trying to minimize this to kind of like fix few at a time. Like because here there are like three variables, three tensors for the variable. You fix two at a time, minimize as much as you can with respect to one of the variables, and then you kind of like go to the next one, and then you go to the next one, and then you do kind of like a back and forth.
So we're really just gonna like take partial derivative of one, take a little step.
Exactly, yeah.
Take a partial derivative of algorithm the last one.
Right. That is like much more has like better behaviors like this. So like a programming perspective, like perspective and everything. But yeah, let's see. Yeah, I think I still have just some time to show you how it looks like. But it's kind of like fun. I don't know. It's just it's a useful excuse also to kind of like get used to how the indices are supposed to be manipulated because it's you're not used to having like such large sums like in other places. So it's kind of like you have to be careful. But again, that's kind of like a lot of it's like in differential geometry or general relativity because you have all these sums like all the time. So okay, so yeah, now we need the term. Okay, now we analyze. You analyze this term as with S. Okay, and again, as with S, now it's like the tensor ABC with itself. So you can put ABC, ABC. And again, like it doesn't matter too much, but let's just put these here with the blue ones so that you see the colors. Those were the original ones, and then I'll connect the others here. Okay, and just as before, I'll call these I, J, and K. And well, I don't think they're the same names as before, but that's like I'm just using the names from my, from my notes when I was doing it myself. M, L, P, Q. Okay. Like again, they're always dummy indices, so you can always call the left, whatever. You can always use whichever letter you want to refer to the left. That's not the point of the dummy indices. Okay, but again, these represents a gigantic sum, right? And if you were to write it down, just as before, it is a sum over I, J, and K, which I'm putting in color just because I do want to emphasize those. And then M, L, P, Q, those are the ones that will end up surviving. Okay, and again, it's kind of like okay, now I kind of like I started here when I wrote it in my notes. So I have A and P. Okay, so A and P, and then you kind of like read this one out. So that gives you B, P, J, Q, V, P, J, Q. Okay, and then the next one, again, if I move this way, I go and then go to C. So C, Q, L, C, Q, L, and then I move to this other C, which would be CKL. And then I move to this one, so that would be with the B. So it would be a B IJK again. And then the AMEMI. Okay, and the important thing to notice is that the B appears twice, so it's not like quadratically B. So when you apply the partial derivative, you kind of like tap into a product rule. No, it is a product rule because you can apply the derivative to this factor or the derivative to the other factor B. That's not something you need to kind of like keep an eye on. So if you want to do the derivative of, again, if you wanted to take the partial derivative with respect to B, I bar, J bar, K bar of this gigantic sum, let me shrink it. Right, it's a product rule. So so it will be a sum of two things. Okay, let me copy paste it first so that you see what's supposed to, okay, and then let me put the partial derivative. So you could have taken the partial derivative of with respect of the first factor or the first appearance of B, and then you do nothing to the second one, right? Let's see. B, P, J, K. JQ, sorry. Right, so you take the derivative of the first factor, do nothing to the second factor, or do nothing to the first factor and take the derivative of the second factor. So that is what the product rule looks like in this case. Let me see if I can move this around so that I have a little bit more room to write down the partial derivative here. I, J, K vars of B, I, J, K. That okay, 70%. Each of these partial derivatives is a product itself,
Yeah.
right?
Sorry.
Yeah, but now you have to be careful because again, like of the matching. So here, right, the only thing that will survive is when you equate P to I bar. Oh, sorry, this should have been like a regular J. Like I shouldn't have put the J bar here, right? Right. So what I'm allowed to delete in the sum. P, I can replace it with I bar, I can replace J with J bar, and I can replace Q with K bar. And here it's a little bit easier because it's just I with I bar, J with J bar. But you can, so let me just write down the sum, the fix, Whew. And then what we would do is kind of like do like a relabeling after we have, but first, like, let me just, again. Okay, so, okay, let's erase. Okay, let me erase this one because it will become 1. Okay, and what went away? P, J, and Q went away, right? Oh my God, this is so easy on the iPad. You have no idea how long it took me to write it down on the. I don't know why I decided to go all fast and write everything on the a notebook because it just takes so much more time to do all these things there. And it's way easier just to do this like, on the iPad because it's just, okay. And then what did I do? I had to, so every time I see a P, I put an I bar now. Okay, every time I see a P, I put an I bar. Every time I see a J, I put a J bar. Okay, that one is not too bad. And every time I see a Q, I'm supposed to put a K bar. So every time I see a Q, I'm supposed to put a J bar. Okay. Okay, a K bar. Yes, thank you. Oops. Oh my God, yeah, you have to be so careful here. Okay. And then for the next one, okay, I, J, and K go away, which again is a little bit easier. Oh, sorry.
Why did you change the A of I?
Oh, of this one you're saying, wait.
No, the first term.
Oh,
The
okay.
first term with A sub and B. And
Right.
then you made it A sub and I bar.
Oh, because the thing is that, okay, so in this part, like, in this Kronecker delta, right? The only thing that survives is when you set P equal to I bar. When it's kind of like a term by term comparison, right? Or index by index comparison, I mean. So P has to be forced to be equal to I bar, J has to become J bar, and Q has to become Q bar. J bar. Like all these words, like getting it. But yeah, it looks a little bit less intuitive for the first one because of like how I call that indices. But for the next one, it's a little bit easier because it's I is I bar, J is J bar, K is K bar, so it's easier. So just remove the. Okay, just remove the IK, IJK, so this goes away. Oops, oh my God, that's not what I wanted to do. This goes away. Okay. And again, this one is a little bit easier because every I becomes I bar. So I becomes I bar, J becomes J bar, and K becomes K bar. So that one was better. Okay. Oh, yeah. Good catch, Chelsea. Good, thank you. Okay, and then what up? Let me put a plus here. Perfect. And then again, you exploit the fact that all of these are dummy indices, so you can kind of like relabel them at will just to make the comparison more easy. So let me see again. Let me just okay. So let's see. I will call. Let me use up some colors. So the index I. There's an I here and an I here. Okay, so I'm going to call I P. I'm going to call I P. So on the first sum, I will just rename I into P. Okay. And what else am I going to do? Let me check with the case. I think that's what the other one I wanted to relabel. So the case, oops. And the case, which I'll do here. So again, I'm just going to change the indices for the first sum. On the first sum, like what I'm calling it. I'm going to call K. I'm going to call K Q. Okay. So I'm going to rename. Let's see if that works. I think it should work. Rename K into Q. Okay, and let's see what happens. So again, I'm not changing any of the names for the second sum, only the names for the first one. Okay, so every time I see an I, I'll put a P. Okay, so now every time I see an I put a P here. And every time I see a K, I put a Q. I put a Q. And again, I became P and K became Q. So now it should be, the idea is that now the indices have the same name, P, Q, and L, P, Q, and L. Okay, let's see if is that okay? Yes, that looks good. And isn't that now the same sum? Yeah. This should be they look the right. So let's do comparison, right? So now they are sums over the same indices, right? And let's do the matching. So M I bar matches A, and these are all numbers, so it doesn't matter, right? Like that's a nice thing about tensor notation when you work with indices, like they are gigantic sums of numbers, so you can just move them around. So this one matches this one, CQL matches this CQL, right? And then PJQ, oh, this was a J bar, right? It's a J bar. So these does match. It doesn't look like a J bar. Let me make it a bit more of like the horizontal line. Okay, now this looks better. So this one matches this one. We're almost there. Right. This one matches this one, and yeah, the other one matches the other one. Right. Which is it's so cool, right? Like because it's kind of like analogous to 2 times x. You know, it's a tensor version of like the derivative of x squared is 2 times x, which is kind of crazy if you think about it, just because there's some many more terms to worry about. So you just end up getting 2 times, right? So this is just like a 2 times over the sum of over m l p q of a m p v p j var q. You know, you just have to keep one of the sums, CQL, CQ var L. Woo, we're perfect time we're almost done, but perfect timing. And that I can interpret, you know, it's basically, let's see, I have so this is 2 times as in the diagram. If you do the tensor diagram, it's 2 times of this thing. That should be the same. So basically there were kind of like two circles, you know, or 2 nodes for B. So you deleted one, but the other survives, right? Like so, because there were 2 occurrences of B. So oh, sorry, this should have been I bar. Where is this? Yeah. Wait. No, what did this okay. Oh, I was called P now. Let me check here. Come on. This is fine, but I think I may mess this up. I became P and yeah, and K became Q. Okay. So it's kind of like, again, if you compare to what we started, then, you know, it has 3 entries, right? Like there's Emacs, so it's also, it has to be a tensor of the same rank order, because otherwise you cannot add up you know, again, the derivatives, like, you know, have to be possible to add it. Yeah.
So same as like at the original thing, it's like you're erasing the top thing.
Right.
Plus erasing the bottom thing. So like I something.
Correct. It doesn't matter which one you. Yeah. In fact, if you cannot relabel them, right? It would have been kind of like which is what you just said, right? Like it would have been just like erase the top plus the diagonal that you get plus from erasing the bar. But I guess it's kind of, which is kind of like elegant, but it's kind of nice to see that you can reconstruct it as a single diagram just twice.
Right, because, but there's some symmetry, right, because like the top level is the same as the bottom level, right, so that's kind of what allows you to kind of like symmetrize it in a way.
And what's the mathematical operation of relation? Does it make sense in terms of like if it's.
Well, you know, there's like it's just really like the it's kind of like similar to when you have like a dot product, right? That you can write it as a sum over I of ui vi, but it's the same as the sum over j of uj vj. I don't think there's like a special name for that except like reindexing. Like I think you would just call that like a reindexing of the sum. Or like, or you would say, oh, the i's and the j's are dummy variables. What I was saying is that in general relativity, like the summation convention is that you just write, you just write this as this. Like you don't even write the sum symbol. The idea is like whenever there are two indices being repeated, they understand that as an implicit sum over those indices. So that's like a very convenient way to, to do it because like it's just kind of like annoying to keep writing the sum, the sum, the sum. So but yeah, I don't think there's any name besides just saying, oh, you just are re-indexing like the sum. Like a change of variable. It's not like a change of variables, right? As well. But it's like a basic change of variables because it's literally just changing the name. Not that you're squaring that one of the variables, or like, So it's kind of like a very basic piece stuff. But I mean, this is very elegant. And then again, like that would give you, that would give you the gradient with respect to the direction of the tensor T. And again, that way, if you wanted to minimize, you kind of minimize the direction, and then you can do like a similar thing. You can find the gradient in the direction of the matrix A, or the gradient in the direction of the matrix C, and then you can kind of like alternate, kind of do partial minimizations one at a time, and kind of go back and forth. I'll try to see I'm trying to find simple enough examples where maybe I'll say like and kind of like give you like the pseudocode or something like that, but you can do it like on a very basic example, and then you just have like the numbers change and everything. But I mean, but it's kind of like important to understand the idea because the gradient is everything for like optimization problems, right? So you do need to know what the gradients are in general. And it is like a very that's kind of like it's also a good selling point for Python notation. It's so useful because it is like a very pretty way of writing it. Instead of like having just this gigantic sum, and it wouldn't be that easy to interpret it. You just write it in that way as a sum, But this is very, very transparent. But yeah, so as I was telling you at the beginning, I still, there's another thing that is important, which is another type of compression. Or factorization, which is called like the non-negative matrix factorization. So I'll tell you a little bit about that on Thursday and next week. And what is a non-negative trend? And which is kind of like a sort of like NVD for matrix with positive dimensions. It's not quite as useful. I mean, as it doesn't have as many nice properties as SVD, but it does have like many applications, probability theory and other places. So I will mention it next time, some motivation about like this latent semantic analysis and like probability joint probability distributions. Like it has a lot of applications to that. So but it's I think a great place to continue to talk about that.